If you had read ahead of time, you probably noticed that the rest of the content in this book is pretty much examples. So MOSFET is, once you master the principle, it's a very simple device. You need to know, like, to understand the trial region, the saturation region, and in the saturation region, you also have this channel effect resistance. So that's pretty much the MOSFET, and then we of course move on to talk about different operating points, how to calculate the current, how to determine whether it's in saturation or trial balance. So it's just different variations. Now I know that some students last time sometimes not too many questions follow. So my recommendation would be one, don't try to copy the equation that I wrote here because it's all like, can also have access. So to focus on listening, try to understand the stuff that we talk. Because when you write, I think it distracts you. That probably really not so effective in terms of understanding. So try to focus to listen. And secondly, I always pause the video. So far we have been able to post every video. Last semester, accidentally some videos were recorded properly, but you can always go back and play the video at a lower speed or faster speed on your needs. Sometimes you need to force me just drag it and then play at 1/2 speed, right? Or you can play at a lower speed to see what happens in that section. So that way you'll have a to material that we cover in this class. I move on. Okay. So we're gonna go through a few examples today, but some of the examples and more examples will be done on March 19th. You know, my TA will give you guys a chance to do more problems. So last week we ended here exercise 5.7. Like in this, what the range of VG for which the transistor conducts? Because you got a one power supply at the top. So if VG is too high, and then VGS not M, that would be different, right? So for example, if VG is 1.8, what happens? Your gate has the same potential as your source. Therefore, that source to gate, that junction is having no voltage difference, right? So therefore, there's no current. So that's the kind of scenario you can think about. So as you reduce VG, so VSG started to increase, and you start to have current. When VSG is larger than VT, you have current. So that is important criteria. So VSG in the PMOS needs to be larger than the threshold voltage current. But you can still be possibly either in trial or in saturation mode. Whether you are in trial or distinguish between what it's a VSG in a PMOS. In this case, it's VSD. VSD is the top, VS is 1.8, and VD SD determines whether it's in child or we call it to be on. But then once that happens, then our VSD can have two scenarios. One is VSD is less than and then also VSD could be, oh no, I call it VSG, not VGS, okay? So VSG minus VT. You know, VSG minus VT is, remember, VOV, yeah? VOV stands for overdrive voltage. So if VSD is larger than VOV, it's in saturation mode. If it's less than VOV, it's in triode mode. And once it's in different mode, the equation to calculate current is different. And for the way to calculate current, so let's say, so if VSG for PMOS, I'm going to mark it here. If VSG is less than VT, then ID is 0. Which is too small. It has to be larger than threshold voltage. If we deny if we SG is larger than VT and it's on, so we call it transistor is turned on, so it would have current or something called conducting. So it's all the same thing, or conduct, which means there's current. Let me draw the symbol here. Okay. If in this case, we'll have two scenarios. One is called VSD is less than VSG minus VT. Or in this case, oh God, we should use so we have to be careful on that. So this is in triode mode, and if VSD is larger than VSG minus VTP, it's going to be in saturation mode. And in triode mode, you remember the arc. So that's the equation. Of course, this equation is a bit complex. You don't have to really memorize it because it's in the book. You can write it down. If it is in saturation mode, then we have the equation totally simplified, and it really becomes just sometimes it can be written also as VOV squared. Okay, so could be negative. Equation most. So when you give the problem, so you get what is VSG for PMOS or for M. So if it is larger than VT, VGS is larger than VT, let's go on to look at what is VDS. Or in this case, what is VSD? Is VSD more than VOA? Yes, saturation. Use the second equation. Not use the first equation, which is the triode mode. So those are the kind of two modes. Okay, so some slides. So this one, detailed is a given. For example, when we say VSG is 1.8 minus 0.5, right? So that's 1.3. So VG has to be less than 1.3. If VG is more than 1.3, then VSG will be less than 0. So that's the first one. Is more than 0.5, then larger than VGS. Equation that VSG is VSG, and then this minus VG. So you go VS cancel the saturation. Erase this one. So for triode, and then let me rewrite this. Let's make sure that we got everything correct. So in triode mode, we have to have VSG, VSD less than VSG minus VTP. So VSD means VS minus VD has to be less than VS minus VG minus VTP. Right? So that's how we separate this VSD and VSG. So VS now cancel. We move VD on this side. So VD has to be larger than VG on this side. So VD larger than VG plus VTP. So this is that equation over here. It says VD 5. If V is larger than saturation mode. So move on, use two following questions. Okay, so we're going to look at another example. So one has solution. You guys can read it later. So a PMOS, and we can write down, says VTP is 0.4 volts. The gate voltage is varied, so VG varies between 2 and 0 volts. So the transistor moves through all its three possible modes, specify the value of VG at which the device changes modes of operation. What are the three modes? Let's repeat together. What are the three modes of a MOSFET? Off, triode, saturation. Okay, I'm going to repeat this again, again. Just it's going to write in your memory. Three modes: triode, off, and saturation. This is a PMOS. So we have to do S, G, and D. So what is in the off mode? What is the condition for this to be in off mode? VSG has to be less than VT. Let's call it VTP here. So which means now we see that VSG is equal to VS minus VG, right? So less than VTP, which is what? 0.4. Now you can move VG on the other side, and we just keep that. So VG is going to be larger than Vs minus 0.4. Now Vs is 2 minus 0.4 means 1.6 volts. Of course, the math you guys can calculate, but the K is to understand that VSG is small, it's too small. It has to increase. So then the next one, so that's number one, right? So number two is it's on. Now it's on VSG has to be larger than VTP, but from the previous section, we already know that VS or VG has to be less than the less. One on, we have a tried mode, and then 2.2 will be have saturation mode. What this will be in tried mode. Mode now let's write. So VSD can be written as Vs minus VD less than Vs minus VG minus 0.4. Okay, so this is our equation here. So Vs apparently on both sides can be cancelled. So we have VD can be larger than VG plus 0.4. Now, actually, if you look at here, VD is given at what? 0.8, right? So VD is given. So which means VG is not given. So what we need to do is to find VG. So VG will be less than VD minus 0.4. And VD is given at 0.8 minus 0.4. So it's 0.4. So what it says that if VG is less than 0.4, this is going to be 2 will be in saturation, which is opposite, which means VG is going to be larger than 0.4 volts. It's going to be in saturation. Tried, of course, you know that if it's that side is tried and the other side is saturation mode. So pretty much the examples in this chapter, the calculations, everything is focused on the off, the triode, and saturation. But as we move on, calculations are a little bit more complex, that it involves a quadratic equation. Once you involve one quadratic equation, the solution. So that's where sometimes it can be a little bit tricky. So we're going to go through some of those examples, right? So you guys can have a better understanding. But when we move on to chapter 7, of course, we forget about this and we move on to the small signal, totally different. Okay, so now we have an MOS. MOS, we can write down the numbers. So VT is given 0.5, VD is given at 1 volt. So this is D, this is G, this is S. I like to mark them down on the diagram so that later when I look at it, I know exactly what I'm looking for. Sometimes you don't write down, it might just kind of confused and forgot about what you're doing, come down. So also K is given. So this K is, so K is the total of Kn prime. K without a prime, that's what it means. And they want you to sketch ID with VG varying from 0 to 1.8 and give equations for the various portions of the right graph. Okay. So basically, we look if yes, because Vs is grounded, that's the same as VG, right? So again, just when you guys do your problem, when you sometimes get confused, just do what I do, just write down VG. So you don't get. I mean, of course, once you get advanced, you don't have to write this more detailed steps. So it's VG, and it has to be, if it is less than 0.5, what happens? If VGS is less than, which is 10, it's off mode, right? Off mode means ID is 0, right? ID is 0. D ID was VG. So if VG is less than 0.5, no correct, off. Okay. So remember, curve ID over VG, not ID over VDS. All right, so let's go to next step. Yes, larger than 0.5. Then mode. It will decide that VDS. So in this case, you guys look at this. So it's 1 volt because VDS is VD minus VS, and VD is 1, VS 0. So you get 1 volt. So this is 1. So VDS is 1, and then we look at if VDS is less than VGS minus VT, it's going to be in triad mode. And a similar example, we want to get this. So VD is same as VDS. So VD less than VGS is same as VG. So this gives you, because VD is 1 less than VG minus VT 0.5. So that means if VG is larger than 0.5, VDS less than VG minus VT, VGS, VG minus 0.5, VD is 1. So if VG is larger than 0.5, it goes to triad mode. So triad mode. So in triad mode, we have the current ID as K times VGS minus VT, VDS minus. So we can plug in these numbers here. So K is given is 2 times, so VGS is same as VG minus 0.5 times VDS is 1 and then minus 1. So that's your equation. So we say that is 2 times VG minus half, 1/2. 2 minus is 1, so minus. So kind of linear. So ID is linear to 2VG minus 2. So if VG is 1, and then that's 0 again, right? So if VG is 0.5, if VG is 0.5, something's not, not right. Which 0.5, it gives you VG2, VG5 minus 1. So if VG is 0.5, this is minus 1. How can we get minus 1? Let's do it again. So if VDS, VD minus VGS minus VT, which is less than 1, which, oh, I see. I made a mistake. 1.5. Sorry about that. Okay. 1.5. Okay. So VG is 1.5, which be larger than 1.5. You know, this to be in if we see how much VG is, because VG started at 1.5. So if we have 2 times 1.5 minus 2 equals to 1. So this is 1. And we keep increase VG, and then this will go a linear relation. This goes like linear up. So this is a triangle. So apparently, look at, we got like the off and the child region determined. So the next point is we're going to get 2.2 is go to saturation mode. Now saturation mode is just opposite of triode, which means we don't have to calculate it. We can simply plug in this number. So VG has to be less than 1.5. So if VG is less than 1.5 volts, it's going to be in saturation mode, right? So the other side, and this side is saturation. So in saturation mode, our current is different. So our current is K times VGS minus VT squared, and K is 2 times, and VGS is VGS is VG minus VT 0.5. So this one you see, this is, yeah, go ahead. Yeah, question.
K is 2 milliamps.
K is 2 milliamps, yeah.
So would you have to be converted before you multiply it by the voltage 0.5?
Yes, it's milliamps. So the K is the right. So you do that. So this is milliamps. Yeah, so yeah, so that yeah, same thing. It gives you so we 1.5, it has to be larger than 0.5. So you know to be conducting. So now your range is between 0.5 and 1.5. So that's your saturation region. Which is 0.5, this equation gives you 0. Okay? If which is 1.5, it gives you 2, which is exactly 2 milliamps over here, same thing here. So this 2 milliamps, and this is good here. So this is the saturation region, trial region. All right. And 0.5, it's in the saturation mode, your current goes as a function quadratic equation from 0.1. And in child region, it goes like a linear relation going up. Okay. So that's this example. So apparently, this is not that difficult, I would say. So yes, go ahead. Uh, 1 squared, which minus 0.5, right? So which one are you talking about?
Like 2VG minus 2.
2 which minus 2, yeah. Oh, you mean that one which is 1.5, that's 1. Okay. Yeah, you're right. 2, 2, 2. Yeah, I look like there's some inconsistency. They should connect at that point. I'll check on this later. Some math we didn't do right. VDS is okay. Two times the 1.5. That I'll look at this. I'll post you guys later. So, but the current one should that should
Question for the graph. So the graph for where the triad would be for the saturation.
also join VG, not VGS. So in this case, when you reach VG, you know that's different. So yeah, so it's different. Okay. So let's move on to look at the other examples. I'll come back to that later to see what happened. So a particular currently is not in the cutoff mode, right? Because you have current. But we don't know whether it's in triode or whether it's in saturation before we look into it. So how do we know whether it's in triode or saturation? Because well, it says it says it has current, so therefore it's not in cutoff. So we know that VGS must be larger than VT. That's something we can conclude, right? Because it has current. So if it's less than, if VGS less than VT, it wouldn't have current. So that's one thing that we can basically already nail down. And secondly, in order to be whether in saturation or cutoff, we need to look at VDS. So VDS typically has to be larger than VGS minus VT to be in saturation mode, right? That's for MOS. That's a condition. So if you look at this example, what can you say about VDS and VGS relations? Equal to each other, right? So then you will say VDS is definitely larger than VGS minus, right? Is something 0.5, whatever the number is, right? So which means we are for sure in saturation. So if VD and VS or if VG are connected, if VG and VD are the same, the device is guaranteed in saturation mode because of the equation here. Because this VDS, because this equation. VDS is same as VGS minus VT, and it has to be in saturation. So this is the equation you can write. This is for the saturation mode. So we're given two conditions. The first one is 360, the other one is 160. So we just plug in these numbers. We're going to get 360 equal to 1/2 K times VGS is 1 minus VT squared. And then the second one says 160 equal to 0.8 minus VT squared. You have number one, number two. So you have two equations. Now, if you plug in the 360 and 160, the value of K, when you solve for it, it's going to be in microamps per volt squared. Microamps. So if you count milliamps, it becomes 0.36 and 0.16, and the result is going to be in milliamps. Just keep in mind what you do on the right hand of the equation gives you the same on the left hand of the equation. I have two variables. In the case of the VT. So if we say two, we'll get 360 divided by 160 divided by 16. So 9 divided by 4 Okay. Times T squared equal to the other side 4, 1 minus 2 VT squared, right? So basically, the reason I want because I do this VT squared. So when you 9 into the VT squared, so if here you got 5 VT squared minus 2.0.8.9, I don't know, 1.44 minus 1.4 VT and then plus VT. Then they were here. Yeah, so this 0.8 times 0.94 plus, and then minus 4. You see what I'm saying? You get this quadratic equation, then you can solve for VT. You're going to have two values. So one value is and which you know that it's not right, only the positive right for this MOS. But sometimes both values are positive, not negative. And in that case, you have to eliminate one. Okay, so that one is going to be either too big or be. Let me ask you, can your VT be more than 0.8? So it cannot be more than 0.8. It has to be 8. And it's wrong. But if it's got negative, you got to redo it. It's wrong. So, but if it's anything between 0 and 0.8, it's probably right. Okay. All right. So yeah. So now we're going to do again do some comparison with the MO. So let's start with the symbol. The MOS we have here. With MOS, with PMOS, you have so this is the basic symbol. It's like flipping a meatball, the MOS together PMOS. Yeah. Mode is off. Position, OSD. Okay. So then we have triode. Oops. This is and then next we're going to go to triode. So once VGS is larger than VTN or VSG larger than VTP, we'll go to the conduction mode. But in the conduction mode, we'll have triode and vision. So in the triode mode, we'll have VDS is less than VGS minus VTN. And here you have with SG is less than, we can use explain, okay, and less than VS. So that's in your triode mode. And then, of course, we lastly get to the saturation mode, and you have VDS. Here you have, oops, sorry, I wrote it down, wrote it wrong. Questions? So I don't have space, so I'm going to write down here. So in this case, ID 0. So in cost, this because again, just want to repeat it for you. CMOS, you have ID equals. Yeah, and then so that gives you this. And I just for the, if we have channel effect, I want to bring this back because if you check back, then we have right second one. So we have the channel effect. Remember what happened is the channel becomes slanted, and the current actually is different from the ones with without a channel effect. Yeah.
For NMOS, since
Yeah.
the current, instead of going from source to drain, it goes drain to source. Is
Yeah.
the current like negative?
Stream source to current this direction. Yeah. Yeah. Drain to source for PMOS, it goes from source we still call it positive, negative, but upward, upside down, and would be negative, but we don't do that. That would be really confusing.
The condition for the channel effect, like what makes that happen?
So the pinched channel effect. So in reality, every MOSFET would have that effect. But for our simplicity, often we neglect it. So which means if I'm asking you to do an example, a problem, I'll tell you whether you neglect or not neglect. If I tell you neglect the channel, the pinching effect, okay, use the equation. Okay. But if I say there's certain channel pinching effect, then that lambda is given, or sometimes VA is given. Remember, this lambda is 1 over VA, right? So if I give you VA, you have to use this equation. So effect is always there, a pinch effect. It's always there. Okay.
That starts to get like tricky.
Yeah. Once it gets like a triangle instead of a rectangle for the channel. Okay. Great. So the next section 5.3 contents. Oh, so there's the all kinds of things. So again, I already compared, so we're not going to go there. Let's do. We still have 10 minutes. Let's both come into in 2 weeks, in 2 weeks, you guys. The reason at that time we have good BJTs and MOSFET, we always compare. Like we do one BJT and one MOSFET, one BJT and one MOSFET. Yeah. Questions? Yeah. So this example, they want to. Sorry, somehow I got a cramping on my toe. Really bothers me, but it's okay. The circuit is good. This circuit is already what we. Okay, what is it? But here, we already practical circuit, we have resistance. And one at the drain, the other one at the source. So if you mark them down, drain, gate. Yeah. So if you look at all the things that are given, it gives you a couple conditions. So that they want you, what do they want to do is find RD and RS so that the transistor operate at 0.2 milliamp and VD is 0.2, and that's NMOS. And also VT is given 0.5, mu COX is given 400, L 0.5, W is 15. So those numbers are already given. You see here, it says neglect the channel length modulation effect. So we are going to neglect it. So it's just, so we're going to go back to. So if you look at the conditions are given, VD is given. VD is volt at the drain terminal. If VD is given, and also ID is given, so ID is 0.2. So from there, we can calculate RD already. We don't need to know anything about the transistor given. So how do you do that? Well, we know that VDD minus VD over RD equal to ID. So ID is 0.2 and VD is 0.2, VDD is 1. So basically you have RD equal to 1 minus 0.2 divided by 0.2, so you get 4 kilo ohms. Okay, so this step you got to do it because nothing about the transistor. What we can do is we can start looking at like this K. So K is Kn prime times WOL, which is equal to the mu n COX WOL, which equal to 400. That's because 0.4 times W is 15 divided by 0.5. That gives you how much? 30, 12. So it gives you 12 milliamps per volt squared. That. We can get the K. So now the next question is, do we know in real life, we don't know VGS because we don't know VS. And also we don't know VDS. We know V, but we don't know VDS. If we have too many unknowns, we cannot decide in saturation or try to. In this case, we have to solve for only tell you the current, but not every voltage. We determine what saturation or in saturation or try more. This is what if you are right, your conclusion matches or done. I'm good. If it didn't, if it was not in that mode, I do this. Once you do that, you don't have to go back to verify. But as a student, you might want to do a verification because, okay, let me see if it makes sense, right? So you say, oh, it makes sense. Yeah, I'm right. If it doesn't make sense, probably you did something wrong. You go back to redo the problem. Now, which mode would you like to assume? Given saturation. Saturation? Yeah, because the equation is simpler. Okay, the equation is simpler. Of course, we always go with the simpler one. And then if we get it, we got it. If we don't get it, okay, let's go back. Whatsoever simpler, right? So assume in saturation. So if we assume in saturation, we back to description. Now, of course, you know that VGS is VG minus VS, and VG is 0. So VGS is equal to minus VS. Or some people say, oh, VGS minus. Well, we don't. VGS might be negative, or VGS will be positive. Now, I tell you, VGS, otherwise, it won't conduct current. So VGS has to be larger than, remember, VGS has to be larger than VT. So don't worry about it. So you'll find VS is negative, so that's okay. We're going to later. Okay? We have this equation, and this equation, so we have Vs basically plus 0.5 squared equal to, how much is it? 0.4 divided by 12. So it's 1/30. Okay? So then we can have Vs plus 0.5 equal to plus minus square root of something. So this step is, remember you put plus and minus sign. Because otherwise you will get one solution, you might say, oh, this is not right. But actually you forget there's one more solution. So once you get this value, you would go back to the equation. And so you have VGS equal to VG minus VS equal to minus VS. And this one has to be larger than VT. If VT, your solution is wrong. So you got that one, right? I mean, so the two solutions here. So one solution here, it's not going to be larger than VT. So you get rid of that solution. Then you have another. Comparison. Okay. Now stop. I did not IS. this class. In some other class, you might actually have some different resistance, okay? All right, any question on this? You guys following? Okay. Now, if you guys don't follow the video at a slower speed and try to understand it. Okay, so this example, and this is MOS. And if you look at the MOS, what happened to the D and S? So when D is active, what do we have for the operating mode? And if you compare VDS and VGS, what happened? VDS. Well, so this is a drain gate for, and then in this is 0. The drain and the gate are connected. Now, since this is in saturation mode, so we can directly go into the equation of directly go to equation of the saturation mode. And in this case, VGS is same as VDS, right? So VGS same as VDS. So VGS, because VD and VG are connected, so we plug in this one to here, we'll get 1/2 Kn prime WOL times VDS minus VG squared. So we can because VT is a constant. So basically, you are plotting. If we're plotting ID and VDS, it's always in saturation. So it yeah, VDS is some sort of value. So then you like this goes to how do you plot it? ID and VDS. VDS minus VT. So okay, I think we have yeah, so this is the same equation that I just let me see how we plot it. So if V is certain value, okay, yeah, I see. So if V at a certain value, and then you can simply just calculate ID at a certain points, but this is a quadratic equation, so ID increase much faster than something like this. Okay. So basically, guys, this equation, we have to imagine with you for sure, but otherwise this equation doesn't make any sense. So when V is VTN, actually it goes to 0. Well, once it's going above VTN, you're going to have this value going, yeah. Okay. Consider the circuit like here. Oh, this circuit is actually the same circuit that we had on the previous slide, but with a resistance connected at the drain. So we want VD to be 0.7 volts, and also VTN is 0.7 or 0.5 volts. C is given, mu C is given, so basically K is mu COX WOL. That gives you 0.4 times, what is it? Times 4, right? So it gives 1.6 milliamp per volt. So that's K. And because this MOSFET in a source are connected, so it is in saturation. And then we have ID equal to 1/2 K times VTS minus VT squared. That VGS, because VDS is the same. So we're going to just have K times VD minus VT squared. And then we're going to plug in all the numbers. 1/2 K is times 1.6. And VD minus 0.5 squared. Find the value of R. So R basically equal to 1.8 minus VD divided by ID, right? Yeah. So once you find okay. So VD ID. Well, how can we find ID without knowing VD? Oh, VD is given 0.7. Okay, I'm sorry. Yeah. So okay. So it's 1.2 times 1.6. Yeah. So 0.7 minus 0.5. So that one gives you ID. So once you find ID, you can find R. So VD is given. It's 1.8 top volt minus the current. Because it's in, so we're able to find the current fairly easy. So here, I'm going to go all the way to just a few words. I know we already have time. So MOSFET scaling, last time I said how much is the size going on, nanometers. So it goes from the 70s, early 70s, all the way to today. It has been following the Moore's law. Every half, the number of transistors double on the same area. And so these are the okay, this table example parameters of different nanometers. But today,